Hello everyone, today in this video we are going to talk about electric field lines of force or simply electric field lines, and after this video you should be able to define what is electric field lines and explain the properties of electric field lines and draw the electric field for different types of charges. So we already know there is a region around a charge where it can exert force on other charges, and outside that region it cannot exert that force, and this region is called electric field. So the region around the charge where it can exert forces on other charges is called electric field. How to represent the electric field? So suppose we have two regions. In one region there is no electric field and another region there is some electric field. So now how to differentiate these two regions? So to represent the electric field we draw lines with arrows, and these lines are electric field lines of force, and sometimes we only call electric field lines, but the actual name is electric field lines of force. Now let's understand what is electric field lines. Now suppose I have a region where there is some electric field, and we already know if we keep a charge in electric field it will experience a force. Suppose this charge moves in this fashion, and if we draw the path of this charge, then that line will be the electric field line of force. So the line in which a free positive charge will move if it is free to so will be the electric field lines. And if we draw a tangent to this path, then we get the direction of electric field at this point. Suppose I want to find the electric field at this point, I'll draw another tangent. Similarly, wherever we want to find the electric field line, we draw tangent, and that tangent shows the direction of electric field. So this is the definition of electric field lines of force, and if we draw the tangent, then we get the direction of electric field at that point. So now we will draw the electric field lines of different types of charges. So first is electric field line of a positive charge. So we will be drawing many diagrams to understand, but we will not draw all the diagrams. So I'll let you know which diagram to draw. So now let's draw for the positive charge. So electric field line is a line along which a free positive charge or test charge will move if it is free. So if I leave one test charge out here, it will get repelled due to this positive charge, so it will go away like this. So if you draw the line, you will get the electric field line. Similarly, I can leave other charges out here, and if I draw all the lines, we get the electric field lines of this positive charge. Now you can see how I have drawn this diagram. So electric field lines are the lines along which positive charge would move if it is free to move. But this diagram is only two-dimensional diagram. So in three-dimensional electric field lines of a positive charge would look like this. So these lines will go in all the direction. So this is also the one. So if you leave the positive charge out here, it would move out here, but if you leave in front, it will come out of the screen. So this is three-dimensional diagram. So this is just for understanding. So this is the diagram you can draw. You can pause the video and draw. So this is electric field lines of a positive charge. Now next is electric field lines of a negative charge. So for negative charge we leave a positive charge out here and it will get attracted, and if we draw the path we'll get the electric field line. So similarly we'll leave many charges around this and this will happen. So if I draw all the lines, I'll get the electric field lines. So you can see this is how I have drawn the electric field lines. But this is again two-dimensional. So in three-dimension it will look like this. So from all the points the electric field lines will go into the negative charge. So out here you can see the arrow is towards the charge. In case of positive charge the arrow was outward. So in negative charge the arrow is inward because the positive charge will get attracted towards this negative charge. So this is the diagram you should draw. So you can pause the video and draw. Now electric field of a dipole. So dipole means two equal and opposite charges separated by some distance. So now if I leave a positive charge out here, it will be repelled by this positive and it will be attracted by this negative. So it will come like this. So this is first line. Now second, if I leave a positive charge out here, so first it will be repelled in this direction and at the same time it will be attracted by this negative. So it will follow some curved path away from the positive and towards the negative. Similarly, if I leave many charges, they will do the same. They will get repelled by the positive and they will get attracted by the negative positive. So they will follow this kind of path. So it will go away from the positive and it will come towards the negative. So this is the electric field lines. So all the charges, first it will leave the positive charge and get attracted accordingly. So this is how I have drawn the field line. So as you consider this charge, it will go this way. I cannot show all the path in the screen, so it will go out of the screen and it will come back. So all the charges will go away from positive and it will get attracted towards the negative. So in 3 dimension it will look like this. So from all the points the electric field lines will come out of the positive and it will enter the negative. So this is another picture in 3 dimension, but you should not draw this. So this is the diagram for a dipole. So coming out of the positive and going to the negative. This line also will go like this. It will go out of the screen and it will come back, and this line also, it will go to infinity, and from infinity either from upward or downward it will come back from here. So number leaving the positive charge must be equal to the number coming to the negative charge. So now next is for electric field lines of two positive charges. Suppose I have two equal positive charges kept like this. So if we leave two charges like this, they will get repelled in a straight line. But if we leave out here, there will be repulsion due to both the charges. So one will try to repel in this direction and another will try to repel in this direction, but the path will be according to these two, resultant of these two forces. So it will follow this path. So similarly, if I leave one out here, so it will follow the same path. And if we leave many charges around two positive charges, they will go like this, and this will be the electric field lines. So you can see how it works. So all the charges are going away from these two positive charge, but it will be affected by electric field of other charge also. So they will form this kind of path. So in middle there will be no lines, but this side there will be crowded lines. So this is 3-dimensional picture for your understanding, but you don't need to copy this. So this is the final diagram for two equal positive charges. Now electric field lines of two equal negative charges. So if we leave the charges out here, it will come straight to the negative. Next, if we leave out here, they will also go straight to the negative charge. Now, but if we leave one positive out here, then it will get attracted by both the charges. But this is nearer to this charge, it will come to this point, but it will follow the curved path because of this. So this is the path. Now if we leave many charges, they will come to them, and this is the electric field lines of two negative charges. So you can see how I have drawn the electric field lines. So all the charges are coming to these two charges, so arrow will be towards the negative charges. So this is 3-dimensional picture. This is similar to that of positive charge, only the difference is arrow, but here there is no arrow. This is just to give you the idea how it look like in 3 dimension. So this is the diagram you should pause and copy. So this is electric field lines for two negative charges. So this is similar to that of two positive charges, only the difference is the arrow. So for positive charges, arrow will be outward, and for negative it is inward. Now electric field line of charged wire. So if you have charged wire, positively charged wire, so electric field line will go away from the positive charge, and this side also it will go. So if we draw all the lines, it will look like this. Now for negative charge, the arrow will be towards the charge. So this is the electric field line coming towards the wire, and this is from another side also, it is coming to the wire. So if you draw all the lines, so this is the electric field line of a wire, but in 3 dimensional it will look like this. So from all the direction, from the back and the front, and from the right and left, so from everywhere the electric field line will enter, or an electric field line will leave the conductor. And electric field lines of plane sheet. So this is a plane sheet, positively charged, so electric field line will be directed away from the positive, and back side also we have. And if we draw other lines, we get this. This is electric field lines of a positive plane sheet, and for negative, just opposite, arrow will be towards the sheet. So this is the final diagram. You can pause and copy. In 3 dimension it will look like this. Now you can draw electric field lines for this. So out here I have kept a positive charge and a negatively charged conductor together. So you have to make the diagram for this system, so they are not separate. You have to start from positive and end at negative. So draw according to the diagrams which we have already drawn. So now the properties of electric field lines. So the field line starts from positive and ends at negative, and if there is only single charge, then starting and ending may happen in infinity. So out here you can see it is starting from positive, ending at negative, but for single point charge, for positive it will be produced at positive, but it will end at infinity. And out here also the electric field line will end at negative, but they will be produced at infinity. So they are coming from infinity, and out here it is going to the infinity. So number 2, tangent to electric field lines gives the direction of electric field at that point. So we already know, if we draw a tangent to the electric field line, we get the direction of electric field. And number 3, the electric field lines never intersect each other. Now let us understand why cannot they cross each other. We already know electric field line is a line along which a charge will move. If I leave a charge out here, it will move this way. Suppose if I have another electric field lines, the charge would move like this. Now if there is a cross between them, and if I leave a positive charge out here, then according to this electric field line it would move in this direction, but according to this it would move in this direction. So it is getting 2 paths, so it cannot decide which path to follow. And we can explain this in another way also. If we draw a tangent out here, so for this electric field line, tangent will look like this, and for this electric field line, the tangent will look like this. So I'm getting 2 electric field lines at one point, and getting 2 direction of electric field at a point is not possible. So if they cross each other, we get 2 direction of electric field, which is not possible. And you may ask why it is not possible. If we have 2 vectors at a point, they will be added up and they will give one resultant. So I should get only one electric field, but there I'm getting 2 electric fields. So now let's see what happens if they cross. So this is one positive charge, this is one positive charge. So if you bring them together, the lines should cross each other, but this do not happen. So what happens? The electric field lines will move away from each other like this. So crossing is not possible. So this is the final answer. with the diagram. So you should draw this diagram for this explanation. Now next property, they are continuous curve without any breaks, so there should not be any breaks because they start at positive and end at negative. If they are breaking, it is not ending in negative, and out here you can see it is not starting from positive, so it is not following the rule number 1. And they cannot form loops. If they form loops, then there is no charge from where they are starting and there is no negative charge to which they are ending, so they should not form loops. Next property is their relative closeness gives the strength of electric field, meaning if they are close to each other, the electric field is strong, and if they are far away from each other, then we have to understand electric field is weak. So out here you can see for 1 coulomb we have few lines, but 2 coulombs we have many lines. So by looking at the numbers of line, we can tell whether the electric field is strong or weak. Next property, they are always normal, means perpendicular to the surface of the conductor. So if this is a conductor, the electric field lines will look like this, not like this. Now let's see why they are always normal. So we know if there is electric field and if we leave a charge in electric field, it will move. So now suppose if I have normal, that is okay. If I have an electric field making some angle, then this can be resolved in 2 components. One is parallel component, another is perpendicular component. So if we see the parallel component, it is going through the charges, and we already know if there is electric field line and if we keep the charge out here, the charge will move. So according to this electric field component, these charges will move. So now the charges are moving, but in electrostatic, that means in a charge conductor, these charges never move. That means we should not have this parallel component. So there will be a surface current, and which is not possible in charge conductor. So we don't see this kind of current. So that means there should not be parallel component. That means there should only be perpendicular component. So all the electric field should be perpendicular. So this is possible, this is not possible. So this is the explanation. Next property, if we have parallel electric field lines, then it represent uniform electric field. Now let's understand how. So suppose I have a positive charge, we know electric field decreases with distance. So suppose out here is 10 Newton per coulomb and out here is 2 Newton per coulomb. So when you're going far away, the electric field is decreasing. If we draw the electric field lines, so I'm drawing only this side because I'm interested in this side. So you can see out here it is more crowded, out here is less crowded. So if we draw this part only, you will get this. So that means out here the lines are more crowded, out here the lines are less crowded, and we already know crowded means strong electric field, and if the electric field lines are not close, the electric field is weak. So now to make the uniform electric field, then I have to draw parallel lines, meaning electric field at this point and at this point is same because the number of lines at this side and this side is same. Out here it was different. For crowded we had more electric field, and for not crowded we have less electric field, but out here there should be equal electric field. Suppose out here I am having 2 Newton per coulomb, so everywhere I will have 2 Newton per coulomb. So uniform electric field means strength is same everywhere in this region, but out here it is non-uniform. So that means parallel lines represent uniform electric field. You can try this question. You have to tell what is the nature of charge A and B, and out here you can see electric field lines are starting from A, so that means A is positive and they are ending at B, so B is negative. And if you compare the number of lines with A and B, A has more lines, that means magnitude of A is more, so the magnitude of charge A is more and magnitude of charge B is less. So And in this question you have to write where should be the electric field more, whether it's point A or point B. So you have to give the reason also. Out here you have to write the nature of A and B, and you have to tell where should be the electric field more out of P and Q, and you have to give the reason for that. And you have to write whether these electric field lines are possible or not. So you have to refer the properties for this. So this is one more. You have to tell whether it's possible or not. And out here you have to draw the sketch for electric field lines. Q greater than 0 means positive and Q less than 0 means negative. And in this question you have to write why the electric field lines are continuous, why should not they have any break. So I think we have already explained this. And in this question you have to tell whether these electric field lines are possible or not, and you have to give the reason. For this diagram you can see they are crossing, and again they are starting from this positive and they are ending at this positive, because out here it's going away also and it is going to the charge, so this is ending at positive. So similarly you can check all others, and there may be more than one reason, so you have to check. Now this is the last question. We have these three charges together. You have to draw the electric field lines for this system. So now we'll quickly summarize the video. We represent the electric field with lines, and they are called electric field lines. And electric field lines are the lines along with a positive charge would move if it is free to move, and tangent to that electric field lines gives the direction of electric field. And this is the electric field lines of a positive charge, this is for negative charge. Only the difference is difference of the arrow. And this is electric field lines for a dipole, and this is for two negative charges, and for two positive charges only the direction of arrow will be different, and they never cross each other. If they cross, then there will be two direction of electric field, which is not possible. And they always start from positive and end at negative. If there is no pair of charges, then they will end or start at infinity. And they are always normal to the surface of the conductor. If they are not normal, the parallel component will move the charge, and this is not possible in electrostatics. And parallel line represent uniform electric field, and when the lines are closed, the electric field is strong, and when the lines are not packed, then electric field is weak.